Okay, we'll kick off again. Roger is going to tell us all about InnerProduct. Over to you.
I'm going to talk about some work I did in Dialog Interpreter, and also in J. The work will be in the next release of Dialog, namely version 12.1, and also in the next version of J, J 7.01. So I'll begin by talking about the way InnerProduct is usually done, and then a different way of doing it, called row at a time. And then I'll describe what the advantages are of the second method over the first. And then I'll present some models of how these methods of doing InnerProducts differ, both in the models are in Dialog, APL, dfunds, and dops, and also in J. And then I'll show some big InnerProducts in J. So first of all, the way InnerProducts are taught in school is that we take a row from the left argument and do something with that, and a column of the right argument. So if Z is the inner product of X and Y, then the ij entry of result is F slash on top of X sub I, the ith column of X against the jth column of Y. A different method is doing it a row at a time. By the way, this is not what I mean by new in all new problem. This one, row by column, I would call it the OO method. And then this is the O method. You can find it in Wikipedia, for example, and also in Bob Bernanke's master's thesis. But anyway, in this method, you do things a row at a time. So the ith row of the result is F reduced over the first dimension of the ith row of the left argument, and then the G function X is 0 on the entire right argument. Now I'll do an example of what this expression does. So this is dialog. I'll just use the existing dialog.
Good idea.
Just to show that there's nothing up my sleeve. Okay, so the expression is X sub I is a vector, so let's do 10, 100, 1000.
Can you increase the font size a bit?
I tried to do it, but it won't do it.
Which font are you using?
Dialog,
Oh, this is classic.
sorry?
This is a classic version.
Yeah, why don't I just use this? The new
It should be a font called dialog symbol.
yeah. Okay, so So there's this expression that I'm going to show an example of. So if you have a vector, 10, 100, 1000, and let's say the function g is multiplication, and then we do x is 0 of 3 by 4 ratio. And then f reduced over the first dimension result. So what are the advantages of row at a time over row by column? So this is row by column, and this is row at a time. One advantage is the cache effects. APL arrays are stored in row major order. So if you're accessing the column, like here, on a large matrix, you could be missing the cache on every entry of the result. Because the first element of the column could be very far from the last element of the column. So whereas here, in the row at a time, the cache effects are very beneficial. And in dialog 12.0 versus dialog 12.1, row by column versus row at a time, and the factor of improvement is 10 times on 600 by 600 matrices. Another advantage of doing things row at a time is that you can exploit zeros in the left argument. That is very easy to see because when you're doing this, let's say you have a zero entry. So if you have a 0 in the left, you know that an entire row of the product is wiped out. You need to do that. So it's worthwhile to check for zeros in the left argument because you can skip over an entire row of work. And first of all, let me do an example of just straightforward.
Does that zero application only work for certain functions, for certain enterprises?
Yeah, I mean 0 in a general sense. That's why I put 0 in quotes. I'm sorry, I should have mentioned that. 0 in the field of operations involving F and G. So it's usually 0, but in other fields it could be something else.
Are you talking about neutral element or something? As in one for multiple neutral?
It's because both the F and the G are involved in determining what exactly what that is. I think you're safe to think of it as 0. Usually 0. So a random matrix, different random matrix. this is 12.1, dialog 12.1, here's dialog 12.0.
You can cut and paste.
Sorry?
I think you can cut and paste if you're trying to do the same thing.
My fingers don't know, can't do cut and paste consistently. Sorry. So there's the factor of 10 improvement from 12.0 to 12.1. And as well, if there are zeros in the left argument, let's say a density of 0.5, say. Do the same here. So it's in 12.1, dialog 12.1, the inner product exploits zeros in the left argument, and here. It doesn't.
It's even longer. Yes.
Yeah, well,
Slow down.
it's, no,
Confused by all the zeros.
small differences are not reliable. Okay, so zero exploitation. It's up to you to figure out which parts are new and which parts are old in this inner product and only problem. Another advantage of row at a time over row by column is that small domain left argument. Or, for example, if the left argument is Boolean, there are only two possible values, 0 or 1. So in this thing I was doing here, how should I express that? Yeah, you're doing x sub I. Yeah. The kth row of the result is that. Right? But if x can have only two possible values, it means there are only two possible results. 0g y sub k or 1y. 1g y sub k. So you can actually, first of all, do g the entire one. Oh, well, actually, basically that. And never have to compute G again, you just look it up if you need it.
So this is really a space-time trade-off.
Sorry?
This is really a space-time trade-off.
Yes, except the space is tiny. Because you've got Boolean elements.
Well,
And,
size of one,
sorry?
it's based on the size of one.
Yeah. Okay, I implemented this idea, this third idea in J, and got a factor of 5. And got better space results, factor of 3 in some cases, factor of 1.5 in others. This exploitation of small domain left order is not in dialog 12.1 because I ran out of time. Ran out of authorized time. But if Boolean inner products are important to your application, you should talk to Morton. Perhaps more authorized time than the other. For various reasons, I think there's another factor of 5 to 8 left in, another factor of at least 5 to 8 left in Boolean inner products in dialog 12.1. Okay, now I'm going to look at some models of these two different ways of doing inner product. This is row by column. As a deal. How do you pronounce it? Dot? Deal? Deal.
Yeah.
Deal.
Is that right, Phil? Yeah.
It's an honest to goodness model because although I've been talking in terms of matrices, it works on arrays of any dimension. And as well, it works on other functions besides plus dot times. It's weird and minus dot greater than or equal. So now I'm going to transform this model into something easier to understand by using components. There's a good quote from Howard Aiken, Ken Iverson's thesis advisor. He says that a system is built out of components, and a component is something you understand. So I'm going to use components to make this into something hopefully easier to understand. So the first transformation is, I'm going to replace this with a defun called flip. Flip just puts the first axis to the last. Next, I'll define another deal called at. It's coming from J, I recognize this pattern as one of the J operators called at. And if your memory goes back far enough, and from the sharp world, you know that the at dyadic operator is also in sharp API. Next step is compose. here, from dot C2 to dot C3, you notice that a function is applied to both, the same function is applied to both the left and the right argument, and then that's what composes. You apply some function to both the left and the right argument, and then you apply some middle function. And then something which currently does not work, but should. The pattern here is that you have composed a function, and then you do something else to it, and then you apply the inverse function, the up arrow, which is the inverse of down arrow. And the J people in the crowd would recognize that as an under or a dual, namely you apply double omega to alpha, double omega to omega, apply a function to the result, and then you apply the inverse function. Okay, so that's what under is.
I think it was called with the sharper tail.
No, it's dual. And if you know where to look, under is everywhere. For example, under anesthetics. You apply the anesthetic, do the operation, and then hopefully you get the inverse, namely waking up from the anesthetics. Now, this is known in J as the hook, and in dialogue as the jot. And that's a prelude to the next step, which is when you have an operator that's in the D-op, if you have if all it is alpha operator expression, which results in a function, and then omega, I don't see why you can't have just the operator expression. In any case, it's a non-zero. Now, I claim that dot C6 is easier to understand than dot C, because what it's saying is that you flip the right argument, and then you split both the left and right argument into rows, apply an outer product to it, that's this part, and then you apply the inverse.
Which are these bugs in Donald that I should worry about, the non-zero?
No, these are things that I hope to convince you to put into.
Oh, right, that was.
Okay, now I'll model row at a time. Here, this is splitting the left argument into rows, and you apply this function to each row in the entire of the right argument, and then you apply the inverse. So I recognize this as an at. Add is what I defined before. And that's about as far as you can go in dialogue, as far as simplification. Oh, let me go back. You may not think of this as a lot short, dot C6 is a lot shorter than .c. But if your metric is word count, then it's a lot shorter. Or if you imagine that add is a single symbol, which it was in Sharp APL, and undo is a single symbol, which it was in Sharp APL, then you know it's a lot shorter.
In .c6, what you don't want the outer braces with.
I'm sorry?
If you lost the outer braces with .c6, it ought to work.
It won't work?
Well, it ought to work if it wasn't for the fact that mix is not the inverse of split.
No, you still have the problem with alpha, alpha, and omega, omega.
Of course you do. Of course you
I
do.
don't know.
Sorry.
I don't know that they can exist outside of braces. Probably shouldn't. Probably shouldn't. Okay, now we go to J. As it happens, flip is short. By the way, dyadic transpose is defined in J. And the row by column, this is how we do outer product, is the dyadic case of slash. So we also, we saw before. Let me just go back to okay. Dot C6 is from before. So we said that it was a flip of the right argument. And then you split the things into rows. You do an outer product. And then you apply the inverse. Or in J, do the flip, and I said that jot was the same as hook, and one variant of jot is the same as hook in J. So in J it's just juxtaposition to indicate hook, and then an outer product, which is dyadic, the dyadic case of the derived function from slash, and then the function itself. I don't have to do the split and then apply the inverse of split because it's just rank. Rank. Maybe applying to vectors of this u slash at b. Okay. Now in the case of row at a time, it's this expression, which I won't explain the details of. I'll just explain one special case of it for rank 0 functions, the most common one that people are interested in. For rank 0 functions, the left rank is 0. So 1 plus the left rank is 1. So row at a time in J is that. An application of rank to rank 1 objects on the left, vectors on the left, or rows on the left, and the entire right argument. And that's rank infinity. And then you do the reduction of that. Now the J here is shorter than the APL because to get these row at a time or row against the entire thing, I can use the rank operator. I don't have to split anything. So because there wasn't any split or enclose, it's here, I don't have to undo it. So I don't have to do equivalent up arrow in J. I'm sorry? Okay. That's less than 40 minutes. Okay, should be okay. Now I'm going to go into a big sparse matrix location. Sparse arrays are a data type in J. And what it is a different internal representation. Here you have a matrix in the representation that you know a rectangular representation. And this expression converts it into the sparse representation, which has the indices and the value of the non-zero values. again, zeros in quotes. So entry was row 0, 1 is 5, so row 0, column 1 is 5. Row 0, column 2 is 9. Row 1, column 1 is 9. And row 1, column 3 is 7. And there's nothing in row 2.
Takes the same amount of space.
I'm sorry?
Takes the same amount of space.
Yeah, probably takes more. When you have a small array like this, it's not really worth it. But then the example won't fit on the cell. Okay, and functions apply to, as befitting the description that is a data type, functions apply directly to sparse arrays. So if you have x, and you can say e to the x plus 1, and give you the answer there. And for the sparse array, you can do the same, e to the xs plus 1. You notice that e to the x plus 1 has no zeros in it, but it's nevertheless going to economize in space, because the 0 element is now what? E. Because the sparse element of the result is the function applied to the sparse element. Now I'm going to do sparse InnerProduct. And while you're watching me type, I just want to point out that dollar means shape. So the x has shape 1e5 by 1e5. SA, the function SA generates sparse arrays of this particular shape with a particular density. So before, in the previous slide, I generated a dense matrix and then I converted it into sparse. Obviously, I couldn't do that here because dense array of 1e5 by 1e5 would blow the thing out of the water. So there's a way to specify a sparse array using by just specifying just the indices and the values, and that's what SA does. And likewise, y is the same. And I'll do InnerProduct. So this is x plus dot times y and j. Yeah. So it did InnerProduct of two 100,000 by 100,000 matrices in 3.6 seconds. And okay, the numbers won't be exactly the same because it's a random matrix, but the number of non-zero rows in X is 100,000. And the number of non-zero columns in Y is approximately 100,000. So you know that row by column is not going to work. Because no matter how fast you are with each combination, there's 1e10 of them. And you do row by columns, you're still doing 1e10 of them, ending up with how many non-zero entries? Only approximately 1 7 entries are non-zero. Yeah. Just a side note, this is some composer cat name on Z1.0. I had to do that rather than just do this, because Z is an array of shape 1E10 by, 1E5 by 1E5. If you ravel it, that's the shape, 1E10, and it's beyond what a 32 bit interpreter can handle. But it's able to, it knows compose a cat. Any questions? Yes, Paul.
What motivated this? Customer demand,
Customer demand
they had some
and,
extra money,
sorry?
they had some extra money.
It was a real application because in input-output analysis, which as it happened was the thing that Ken did his PhD thesis on. In input-output analysis, you can get huge matrices. And by necessity, huge matrices are sparse. You don't have enough data to populate every entry. Or if you spend $1 here, it's not going to have an effect on every part of the organization or economy. So that's what I'm doing. Besides, it generates a cool demo. I did a huge inner product.
That's your motivation. What theirs?
But can you have nested sparse arrays?
Not currently.
Because I'm thinking sometimes in various sort of far distant parts, you would have different zero values, like you have the E and the 0. But
Okay.
yeah,
No, that's not nested. That's
no, I was
Something
thinking, I
different.
mean, you could solve that problem with nesting, so I'm giving you
Yeah.
a solution rather than a problem.
no. No, it's. I think you get into very nasty problems. Like you can have a. Yeah, you can have a billion element vector. You can do things with it, but you cannot do the grade.
Yeah.
Because although you can do the sort.
That's interesting.
Yeah.
Having got a sparse array, you produce a sparse array. You've got an array which is sparse. So you produce a sparse array from that. You've got one sparse element, or also one element which is the sparse element. Could you then do a sparse array on your result? Because 0 is the most common element in the sparse array. Then you may have a value of 1, which occurs 90% of the time. So you have a sparse array of a sparse array embedded.
You're right. Both your question and Gita's question, I would,
Of the same.
Gita's version is a simpler version of what you're suggesting. I would tend to shy away from
Right.
having sparse elements in it, more than one element. The order of complexity, I think, will increase
Exponential.
dramatically if you have two different ones.